An alternating series is where the signs alternate, like it goes plus minus, plus minus, plus minus in between your terms right there. Just because you have an alternating series doesn't necessarily mean that you're going to use the alternating series test, but it means that it is an option. All right. There's a couple tests that we're going to learn in the next section here that will also work on an alternating series, but there will be things inside of those original problems where I'll tell you, hey, when you see this, hey, we're going to do this test. When you see this, we're going to do this test. But pretty much if you have an alternating series and it looks pretty basic, pretty straightforward there, alternating series test has a really good chance of working. All right. So the most times you see an alternating series, you'll see like the notation -1 to the n or -1 to the n plus 1. Let's talk about why it's going to cause it to alternate, right? Like if I plug in 1, you have -1 to the first, which is a negative number. And then if I plug in 2, you have -1 to the second, which is a positive number. So when you plug in the numbers, the signs are going to alternate right there. So a lot of times you will see that notation in the problem that tells you it's an alternating series. There is one other thing that could happen in the original problem that I'm not going to tell you right now that happens in the homework that will cause it to alternate. All right, that will cause it to change sign from plus to minus or minus to plus and keep switching sign right there, in addition to the -1 to the n or -1 to the n plus 1 notation. Again, just because you see that doesn't mean you're going to need the alternating series test. But I will tell you, when you see that notation, it looks pretty basic like these couple of problems there, then alternating series test will most likely work on these problems. All right, so anyways, there's two little, I got them separated, whether it's going to converge, whether it's going to diverge, all right? But this is all your alternating series tests. When you want to show that it converges, you need to show two things. That's why I got that giant word "and" right there. We need to show that two things are true. The limit as n approaches infinity of the a sub n. Now, the a sub n is just the formula part of the problem, the positive part of the problem. The a sub n on this one is just 1 over ln of 3n plus 2, not that part that makes it alternate. The a sub n on this one is just the n over 2n minus 1, just your main formula part, not including that notation. So when you're working out these problems, don't include that notation when you're working these out right there. That's falsified there, and then your inequality might be messed up. You might be saying something's true and it's not true, right? So again, your a sub n is just 1 over 5n plus 7, not the -1 to the n plus 1 notation. So when you do the limit as n approaches infinity of that a sub n part, and you get that's equal to 0, that's one part. Don't just stop there. You got to also show that a sub n plus 1 is less than a sub n. Now, we're going to see this notation in the next section as well. Let's just talk about that. That stands for like the next term, okay? And so the next term, here's what will always work for us. And this will make more sense when we do this in the problem. This won't be difficult. A sub n plus 1, what will always work is if you replace your n with an n plus 1, that's always going to get you like the next term. If you show that both things are true, then that's going to converge, right? So you got to show that two things are true to prove convergence. And the nice thing is we don't have any inconclusive stuff to worry about on this alternating series test. If you do the limit as n approaches infinity of that n term, that a sub n, and you don't get 0, you do that limit as n approaches infinity, and you get anything other than 0, that should ring a bell. That will prove diverge. That is really just your nth term test. So if it is an alternating series test, it's part of your alternating series test. You can use alternating series test as your reasoning, but if it's not an alternating series, you'd have to use the nth term test right there. All right, so let's do a couple examples. And so what I did, you don't have to do these on these problems there, but what I did, if I plugged in 1, then plugged in 2, then plugged in 3, it went a negative, positive, and a negative. And if I plugged in 1 there, I got the ln of 5. I plugged in 2 there, I got the ln of 8. Or I plugged in 3 there, I got the ln of 11. So I did that. I plugged in 1, plugged in 2, plugged in 3, and I wrote down the first few terms of these sequences here just to let you know that it is alternating. And I wanted to show you something with the pattern on some of these where a common mistake comes from. All right, so here's how it's going to work there. So once I recognize I can use the alternating series test, I'm going to follow this up. So I'm going to do a limit as n approaches infinity of a sub n. So I'm going to do a limit as n approaches infinity of the a sub n, which is just the formula part, the ln of the 3n plus 2. All right, so when you plug in infinity, we should remember that ln of infinity is infinity. So when you get 1 over infinity, that is equal to 0. So that's just the first part of that. Please don't stop there. And then you also got to show that a sub n plus 1 is less than a sub n. Common mistake is when people do the a sub n plus 1, they want to write down 1 over ln of 3n plus 3. Like they'll just go to that and add 1 to that. But if you look at the pattern, see when I plugged in 1, I got the ln of 5 on the bottom. Then when I plugged in 2, that next term, I got the ln of 8 on the bottom. I didn't just add 1 each time. You're adding like 3 each time to that ln part of the problem right there. So the thing is, we're going to use this in the next section as well. We'll have factorials, we'll have sequences, we'll have a bunch of stuff. What will always work is right here. When you do that a sub n plus 1 part, replace the n with an n plus 1. Again, ignore that negative 1 cm notation. We're not doing that. All right, that just tells us we're allowed to use this alternating series test. So I'm going to go ahead and finish it. So a sub n plus 1, I'm going to go 1 over, right, because this right here is the a sub n. So all I'm going to do is replace that n with an n plus 1. And then when I replace that n with an n plus 1, it's going to look like this, right? So I just replace that n with an n plus 1, everything else carries down. So this is your a sub n plus 1, and then you can distribute that. That'll be 3n plus 3 plus the 2. You're going to get 1 over the ln of 3n plus 5 right there. That's representative of your a sub n plus 1. That's the next term in that pattern. And if you think about it, if this is your a sub n, and you notice how we kept adding 3 to those, look what happens when I add 3 to that, I get the ln plus 5 there. So a lot of times people just put, like, they go to that, they add 1 to that, they put a 3 right there, got to put it, plug that n plus 1 in place for the n, distribute out, that's your a sub n plus 1. And we need to show us that's smaller than the a sub n. So I'm going to write down that's less than the a sub n. That's the original formula part of that problem. Now remember, just like when we did the direct comparison, if you want a little more instruction there, you can't just write it down. Just because you write it down doesn't make it true. So this is the exact same thing though as your direct comparison notes. You need to justify why this is true by doing that one key step. We're going to do true since that 3n plus 5 is greater than that 3n plus 2. So that justification works when those numerators are the same right there, and that plus 5 is bigger than that plus 2. So once you show that the limit was 0 and you showed that the n plus first term is less than the nth term, and you justified why that was true, you have successfully shown both things. So all that work is your answer, and then now we're just going to finish it up. That proves that it converges. So we're going to get converge for this one, and the test that we're using is the alternating series test. You can abbreviate like that. Don't just put like AST or something like that. I don't know what that means, but you're gonna put converge or diverge. Tell me the test that you're using there, alternating series test. All right, next example. I see that, and it looks pretty basic. I see that it looks pretty basic. So we're going to do alternating series test on this problem as well. So I'm going to do the limit as n approaches infinity of the a sub n. The a sub n, again, is just this part right here, not including that. So don't include that in there. All right, that's going to mess up that inequality sometimes there, and you're going to throw yourself off, right? So don't have to worry about that. But we're going to do the limit of that thing. And we're going to evaluate that limit. So the degrees are the same. That limit answer is equal to 1/2. So I don't get 0 for that. So I'm looking right here. So if you do the limit as n approaches infinity and you get anything other than 0, that's going to prove diverge. So we're going to put diverge for that. Now you got an option here. This was an alternating series, so you could use your reasoning. This is part of your alternating series test. Or, okay, that is your nth term test. When you do a limit as n approaches infinity, you get anything other than 0, you could also use your nth term test right there. So if you wanted to be safe, you could always use your nth term test because you could only use alternating series if it's actually an alternating series. If it's not an alternating series, you can't put alternating series down for that reason. You would have to put that nth term test there. But there's an example of something that diverges, and you just got to give me one of these reasons. You don't have to give me both of those tests there. All right, and I think that's pretty much good for our notes there, but just to give you a little thing, because sometimes I see people do weird things when they turn this homework in. So I feel better if I just do one more example with you. Again, if you plug in the 1, plug in the 2, plug in the 3, those are the few numbers that you're getting to start out that thing. You don't have to do that, but I'm going to apply the alternating series test here. So we're going to do a limit as n approaches infinity of the a sub n. So that's 1 over the 5n plus 7. And then notice that that's like 1 over infinity. That's, you know, that's like n over n squared or n to the 0 over n to the first. The degree on the bottom is larger. So that's 1 over infinity. So that's equal to 0. So that's the first part of that thing. And then you also got to show that the n plus first term is less than the nth term. So you're just showing all this stuff is just like decreasing, right? So a sub n plus 1. So when I do a sub n plus 1, I like to kind of just well, I'll just write that down here. There's your a sub n plus 1, and I got to show it that is smaller than the a sub n, than the original one. So we should multiply this out. This would be 5n plus 5 plus 7. So I get 1 over 5n plus 12 is less than that 1 over 5n plus 7. And then, you know, I'm hoping that you guys just do that. Like I said, a common mistake when people do the a sub n plus 1, they'll have a 5. They'll just go to this and add 1 to that, and they'll put a 5n plus 8 right there. And notice it doesn't go 112, 1 over 13, 1 over 14. Those denominators are not going up by 1 for that to make any sense for us, right? Now, if they were, then you would go up by 1, you know, but those are going up by 5. And notice if you take this and add 5 to it, then you got that plus 12 there. But most of the time, we don't have the need to write all that stuff down to see what it's going up by each time, but you could just, you know, what will always work is if we replace that n with an n plus 1 and get good at that, because that will not disappear. That will be in the next section all over the place as well. So around this part, we have that written down, but just because I write it down doesn't make it true. But we know that 5n plus 12 is bigger, so you have to write this down. This is not like an optional step. You have to write down true, since that 5n plus 12 is greater than that 5n plus 7. So please don't be lazy with that notation. Everything I'm writing down here, with the exception of that, everything is necessary. These are like proofs. You're proving that these things converge or diverge. So you got to be pretty technical. I'm going to be pretty picky about that, but you got to justify why that's true. So we got the limit is 0, and we have this written down, and we justify that that was true. So those two things acting together proves that this original series converges. So we're going to get converge, and then the test we're using is the alternating series test.